This is the third video on naming and writing the formulas for the compounds that you'll be working with this year in chemistry. In this video, I'm going to be talking about naming and writing formulas for acids and bases. Acids and bases are particular kinds of compounds. They have certain properties when they are in aqueous solution. Aqueous means they have been put into a solution in water. They have been dissolved in water. In aqueous solution, an acid will donate a hydrogen ion. It will give up a hydrogen proton, no electrons attached, so it'll have a positive charge. And bases are a substance which will accept that hydrogen ion. We've worked with the pH scale a little bit already in lab, and the pH scale is actually a measurement of the hydrogen ions that are present in that solution. So a pH with a number that's less than 7 is classified as an acid, and the lower the number it is, the stronger the acid. A pH that is greater than 7 is classified as a base, and again, the higher the number, the stronger the base. And then exactly in the middle at 7 is considered a neutral solution. There are other types of acids and bases that you probably will learn about if you go on in science and take some more advanced chemistry courses, but you don't need to worry about them for this first introduction to chemistry. There are some other characteristics of acids and bases I thought I'd go over while we were on the topic. Both of them are electrolytes. They make ions and they will let electric current flow through them in solution. So because they make ions, they can carry that electrical current. Acids taste sour, and a lot of the foods that we eat do contain acids. Of course, our fruits, our citrus fruits, have citric acid, and that might be something you're already aware of. But some of our other foods also have acids. The beverages, the carbonated beverages we enjoy, are part of their taste appeal because of a slightly sour taste. We don't have so many things that are high in a base ingredient because it has a more bitter taste, and so it's not quite so appealing, and it also can typically be a little more dangerous to our human body, so we avoid those foods. Litmus paper is a way of testing the pH, so acids turn litmus paper red and bases turn litmus paper blue. Another test for an acid is that it will react with certain metals to produce hydrogen gas. So in that case, the hydrogen that is donated from the acid actually turns into gas and leaves the container. Bases react to create a slippery feel because basically they are interacting with the fatty acids that are present on your skin as you give off a little bit of oil to keep your skin lubricated. The bases and the fats make soap, which is actually how you make soap, and so they feel slippery on your fingers because you're making a very thin layer of soap right there on your fingertips. And then acids and bases will neutralize each other. You combine just the right proportions of an acid with just the right proportions of a base, and the pH will go to neutral or 7. So, naming acids. Well, all the acid formulas that you will be working with this year will start with an H. Not every compound that starts with an H is an acid, but most of the ones that we're dealing with will be. So 2 examples I give you here: HCl, hydrochloric acid, H2SO4, sulfuric acid. The rules for naming these acids depend on what type of anion is following that hydrogen cation. So the first set of rules are for binary acids, or acids made of a hydrogen and then some kind of "ide" ion. The rule for naming it is you start with the word hydro, add the anion ion prefix, depending upon whatever that was for the original element that name came from, and then add "ic." So our HCl that you've already heard about, you have the hydrochloric acid. So hydro plus the chlor as the anion name prefix from chloride, and then ic, hydrochloric acid. HF would be hydrofluoric acid because it's containing fluoride ion. H2TE is the hydrotelluric acid because it's the telluride ion. And then H2S, hydrosulfuric acid. Notice that we're using the whole whole word sulfur instead of just a shorter version of that like sulf. I think it's because they wanted to get everything to end in R. It seems to be a very common pattern that they use the prefix so that it ends in an R before we add the ic. Incidentally, cyanide is the polyatomic ion that ends in ide. It's the one polyatomic ion that doesn't end in H or ite, but ends in ide. So it follows this particular rule, even though it isn't a binary acid because you have 3 atoms in there, but HCN is hydrocyanic acid. Then our next group of acids are the oxyacids. And so this is an acid made of hydrogen and a polyatomic ion which contains oxygen. If the polyatomic ion has a name that ends in ate, then there's one set of rules, and if it ends in ite, there's another set of rules. So if it's an ate ending, you have the ion name, so there's no hydro or anything in front of it, but just the ion name prefix plus ic. So H2SO4, SO4 is your sulfate ion, so that's an ate ion, and that makes sulfuric acid. HNO3, well, NO3 is your nitrate ion, so we have nitric acid. And then H3PO4, PO4 is your phosphate ion, and so this makes phosphoric acid. Notice that we're using phosphor as the prefix when we're working with phosphorus. If that polyatomic ion ends in ite, then you use the prefix for the ion plus OUS to talk about the type of acid. So instead of SO4, if you had H2SO3, SO3 is the sulfite ion, and so this makes sulfurous acid, not sulfuric. So paying attention to the endings on the polyatomic ions is pretty important. Similarly, HNO2, NO2 is nitrite, so this makes nitrous acid. Bases are a little bit simpler because all the bases that you will be working with are going to contain the hydroxide ion, which is the OH with one negative charge. And you just name those bases like any other ternary ionic compound. So NaOH would be sodium hydroxide, just the name of the first element, the cation, plus the name of the polyatomic ion. CaOH2, calcium hydroxide, again, the same rules. Ammonia is the one exception that you're going to need to memorize it. I already mentioned it as a common compound that you just need to remember the name because we don't name it like a covalent compound. And so NH3 is ammonia. So this covers the basics for naming acids and bases, the stuff that you need to know. Put that together with the information on naming ionic compounds and naming covalent compounds, and all of those chemical formulas should start to make a little more sense to you as you look at them from this point onward.